Wonderful. So welcome, everybody. We are very happy today to have Quoc Ho here to tell us about higher representation stability of generalized configuration spaces.
Okay, thank you very much for the invitation. It's great to speak here today. So yeah, so I'm going to talk about higher representation stability phenomena for generalized configuration spaces. So let me start with kind of the motivation. So like I'm sure that everyone here is probably more familiar with this than me, but just to fix the stuff, let me start with kind of the basics. So stability phenomena. Okay, so let me start with the simpler variant I'm talk about, namely just homological stability. Homological, right? Okay, so the situation where I work in is going to be, suppose you have a sequence of chain complexes. So C1 up to C2. So it's a bunch of chain complexes. So each of the CIs is a chain complex. So this is not, what I'm writing is not a chain complex, but it's a sequence of chain complexes with map between them. So CIs are chain complexes. Since I'm talking to a topologist audience, I want to emphasize that I'm using cohomological degree convention. So D goes up. Okay, so suppose I have a sequence of chain complexes like that. So these chain complexes appear naturally somehow, and then that will induce for each I a map from HI to HI of Cn plus 1. In many cases, somehow we see that this is an equivalence. This is an isomorphism when n is very big compared to I. So this sort of thing is called homological stability. So the CI that I will care about are called the cohomology. So let me do n here of m, where m is a manifold. Where this, so everyone knows, but so this is the nth power of m minus the big diagonal, so all the stuff that have two coordinates being equal, and I mod out by the symmetric group Sn. Right, so this cohomology, this is I think it's quite well known. This sequence, you have a sequence like that, and you have this phenomenon for configuration spaces. Okay, and in practice, the range. So even though I wrote like that, but in practice, stability range can be computed, or at least approximated. Right, so the picture I want to give for this. So again, I'm very sorry, but somehow I choose a different convention from how people usually draw this in the literature, and somehow I cannot switch it in my head. But K is to indicate where it is in the sequence, and C is the cohomological degree, and the maps are like this. And so that after some step, the map becomes equivalence or isomorphism. So that's the picture that one should keep in mind. Okay, so the question that we want to study is what happens outside of this range? So outside of the range where stability happens. Okay, so model is that the failure of homological stability themselves or itself, in many cases, exhibits stability. Okay, so let me say what that means. So I guess this phenomenon was first, so again, people here probably familiar with the literature better than me, so please correct me if I'm wrong. So I think this phenomenon was first and Brander will. So let me say more precisely what that means. So you have a map from Cn minus 1 up to Cn, and then you measure the failure of stability. So that's measured by the cone of F. Right, so the cone of F is whatever it is, such that when you take cohomology, you get the log exact sequence of cohomology. So that's precisely measure the failure of homological stability. So let me call the cone of F. Let me name this C prime n, just tentative notation, C prime n. And so in many cases, you can actually provide maps. So we can construct, sorry, but can construct so like this, C prime n to with plus the number L, say H, and C prime n plus K. Sorry, not n, yes, n. Yes. And so note that the difference between this map and map above is that, so above, right, I is fixed. So cohomological degree just stays fixed. And the only thing that increases is the number n. Here, right, the cone can go some number h, and the number n can go with some number k. So it's some math in a kind of not vertical, but some other direction. So I want to visualize something like this. This cohomological degree. And in many cases, this map itself is for each fixed I, then somehow you have hi plus th c prime n to hi plus t plus 1h c prime. Sorry, I made a mistake. It should be plus tk. Okay, so this formula looks confusing at least to me, but whatever it is, it's just like I'm just saying that when you go far enough in this thing, you get an equivalence. So after some cutoff, t is very big. All the math after that are equivalences. So what they call secondary stability. Right, so secondary stability. Okay, so we can actually, I guess we are greedy, so we can ask for more. So we can ask, what about the failure of secondary stability? Does it exhibit like third level stability as well, and so on? So I wouldn't say precisely what it is, but I would say that we want to ask even more higher. Okay, very good. And now let me actually make a reformulation that will motivate what comes next. So let me reformulate what I said above. Okay, so the usual thing that we like to do in this game is to put all the Cn together to some big object. So instead of thinking of doing this game, C1 not to C2 and so on, we want to put some C that is a direct sum of all the Ci. Okay, and I call it C. So this is so let me know this the category of such thing. So it's a graded chain complex. So it's a bunch of chain complexes with the grading. And then I encode the map from Ci to Ci plus 1, which is a degree 1 map. So that structure is given by, so C has a structure of a CX module, where CX is a polynomial algebra, a graded polynomial algebra, where X is in graded 0. Right? And you see that I'm just reformulating these maps. So multiply by X, give you the map from Ci to Ci plus 1. And so now I want to formulate this this cone thing that I mentioned about. So I have this map Cn plus 1, right? And I took the cones. And now I want to look at this object C prime. This is the direct sum of all the Cn prime, right? All of them. And I want to formulate C prime as some natural object coming from Cn in some sort of like commutative algebra kind of way. So in fact, this is actually very easy to see. This thing, C prime, is precisely C tensor with C. Yeah, I guess this is pretty unfortunate notation. So this C is my chain complex, my graded chain complex, and this C is a complex number. And I do the relative tensor over Cx. And again, so in this talk, everything will be derived automatically. I won't usually people write L there. I won't write L anywhere. Everything's automatically derived. So you can see this easily by knowing the fact that C as a CX module has a 2 resolution given by free module multiplied by X, and then tensor just commute with taking cone. And so this is cone of C mapping to C plus 1. And so that's our C prime. And then the next step, right, to formulate secondary stability is about equipping C prime with some extra operator. So C prime, so we want to equip C prime with the structure of some CY module. Again, everything is graded. Where Y is some homological degree, I guess. Homological degree H and graded degree K. And that would be the structure that we use to witness and formulate what secondary stability means. And then we can keep doing this sort of thing. We can validate the tensor, and then we can ask the next step, and so on. So that's what I mean by higher homological stability. Okay, but the topic of the talk today is not homological stability, but rather something called representation stability. Okay, so I guess this is in fact the title of the seminar. So please forgive me if I forget someone's name. So people like just like Church and Ford, Ellenberg, and I guess Putnam, and Sam was, I guess, one of the people who started some of the people who started this business, and there are many others. And I hope I didn't offend anyone. Okay, so representation stability is essentially homological stability, but with group action taken into account. So the previous example I had in the first part was unordered configuration spaces. So you see that I take this power and then remove some stuff, and then quotient by the symmetric group. So suppose I don't take the quotient by symmetric group, and I take cohomology immediately, then these cohomology group will be equipped with the actions of these SIs, the symmetric groups themselves. So roughly speaking, you have these chain complexes like before, but now each of the chain complexes have action. Again, this can be generalized in many ways, but I will only focus on the case of symmetric group acting. And you ask that these maps are compatible with this action in certain way. And then in this case, you can do this game. So you have to take cohomology. You do this game. And then we want to say something like this. for example, we want to say that up to Si+1 action, this map is surjective when K is big enough. So surjective up meaning that you look at the image and you span it by Si+1. And then spread out what the compatibility is, but the data that is involved is something called an Fi module, where Fi is the carrier of finite set with injections. And the one that I really care about is the Ci is equal to cohomology of order configuration spaces of some manifold M. And C star is the cochain complex. Okay. So now higher representation stability. So what does that mean? So again, I want to reformulate this thing. So we know that Fi module. So I think this is a theorem. Yeah, gosh, I think it's a theorem by Putman and Sam, and maybe Snowden as well. So I should have done my homework and remember who proved this, but in any case, this is not something I do. So Fi module are the same as Cx module. So let me say precisely what I mean by this. So first of all, consider the current Fb. So finite sets with bijection. Oh, actually, yes. Actually, I have it in my notes. So this is by Simon Snowden. Okay, and then I look at the category of FB module, which is the category of functors from FB to vect, where vect is the category of chain complexes. And this category has a natural monoidal structure given by convolution. And so I can talk about commutative algebra objects inside this thing. So I would denote the category by com out in vect FB. And then I look at Cx. By definition, it's the free commutative algebra generated by one object, by one dimensional vector space in graded degree 1 and cohomological degree 0. So that's Cx. And then the result says that Fi module is the same as Cx module. So Cx module object. So if I want to be very pedantic, Cx module object in the category of Fb module. So that's the result of Sam Snowden. Okay, and now I want to measure the failure of representation stability. And so we look at the same things above. So let's see with such an object. So again, everything is actually derived. So these like chain complexes of Fb modules and so on. And then what I do is the following. So I take C, Cx, and then C. So it's exactly the same as before. And this is something people call Fi homology. But if you want to emphasize the fact that C is a chain complex, then people also call this Fi or hyper Fi homology or Fi hyperhomology. But I will not say the word hyper. For me, Fi homology is this. And so higher representation stability, or at least in this case, secondary, is about equipping this guy with more actions, with actions of some commutative algebra object in vect FB, and then study when they surjective and so on. Okay, so I want to give a remark that. So I guess two remarks. I guess one remark, two items. So this sort of question is was first considered by Mueller and Wilson for order configuration spaces of open manifold of dim 2. And then later on, there's also work by maybe in Garish for orbit configuration spaces. So these are the because the two main works that concern higher representability for configuration spaces. Okay, so let me, before saying anything further, let me actually state a concrete result that come out of this sort of studies. So let me state the theorem. So let X be connected, non-compact manifold of dimension at least 4. Then there exists a function, let me call it R, from, so that tends to infinity, such that when K is greater than P minus RK, then the image or the images of the action of H0x and H1x on HP of P conf K minus 1x and HP minus 1 P conf K minus 1 x span HP of K conf K x up to SK action. Right, so usual homological stability, you have just the action of H0 on this guy, and you know that when K, so essentially there's no more is K greater than P, then you get this statement. Now, with second stability, we can say something like, okay, if we are allowed to use more thing to act, then we can improve it compared to the usual result. Okay, so that's one concrete result that you can prove using what I'm going to say next. Okay, so let me say what actually goes into this theorem. So I guess two things is that the homology of P conf X. So when I have no index, right? So usually a P conf K or something. When I have no index, means I just take a union, disjoint union of all of them together. So since the homology of P conf X is a free Fi module. So I think this is so for non-compact. For non-compact manifolds is the theorem Church-Ellenberg and Ford. And so because of this, Fi homology will just give you the generator. Just recover you for you the generator back. And then the second ingredient that goes into this theorem is explicit range for the generator. Right, so the generator is is given by some graded chain complex. We want to know where it's supported, like homological degree wise and also graded degree wise. So the goal of this talk. So we want to consider non-smooth case. In fact, we want to something that we work for, even say schemes. Something even for schemes. And then second, we want to also consider generalized configuration spaces. Instead of just configuration spaces. So by generalized, I mean the following. So usual configuration spaces, you look at powers of the original geometric object, and then you just remove everything that has multiplicity greater than or equal to 2. Generalized configuration spaces means that you look at the power of the original geometric object, and then you say that something like, I only remove points of multiplicity at least 5 or something, right? So that's what I mean by generalized configuration spaces. And we want to also do higher representation stability. Right, so this concrete theorem that I quoted above is essentially only concern secondary stability. Okay, so this is the goal. So what is the approach? How do we study this? So before doing anything, let me introduce notation. So I would denote K n x. So n is a fixed number, k is a fixed number, and xk. So it's the power part. And the minus, I call it delta n. So delta n is the part where you disallow points of multiplicity greater than or equal to n. And if I don't have the k there, then this thing is just disjoint union for the p. And so, for example, p conf k of x is by definition just pk2 of x. Okay, so this is this notation. And so now, okay, so how do I approach these questions that are posed in the goal? So the strategy is to equip C star, so the cochain of P and X with the structure of an object in this. So wanted to have the structure of a commutative algebra object in the carrier of FB modules. So these have a name. So these people call this twisted CDGA, differentially graded algebra. Okay, and then all the actions. So whenever in algebra, right, you can always fix an element in it and then act on your thing. And what I'm saying is that all the actions used to witness or higher representation stability come from multiplication. You pick some element and then so once you have such a thing, then you can compute. You can try to compute explicitly, or at least approximate, the support of its generator. So these are the higher analog of Fi homology. Okay, so this is kind of the very broad stroke of what the strategy is like. And the main tool we use is something called fertilization homology and causality. And so in the next part of the talk, I will recall what these are and how they're related to our studies of higher representation stability of generalized configuration spaces. Okay, so let me start with the untwisted case, because it's the same, but somehow psychologically it's easier to see what's happening. So untwisted meaning that I'm not doing any of the FB module, just plain chain complex. Okay, so what I want to write out now is essentially apply whenever you have the theory of the geometric theory along with some sheaf theory that satisfy enough functoriality. So in general, suppose you have X up to a point. So X can be a scheme, a manifold, or a nice topological space. And let me call. And then you can consider the carrier of sheaves on X. So by sheaves, I mean constructible sheaves. And then there's a pair of joint functors. One is pushing forward with compact support, and one is pulling back exceptional pullback. So if you're not familiar with this theory, then you can think of X as being, say, smooth and compact. Then anything, but essentially when you start with the chain complex, or just say a vector space, and you just have that as a constant sheaf on X, put it in some cohomological degree, and then F lower strict is just taking cohomology. So essentially, when X is non-compact or non-smooth, then it's something more complicated. But when it's smooth and compact, then it's just reduced to what I just said. Okay, and then the category X has a monoidal structure slightly different from the one that you're used to. So something called monoidal. So there's some monoidal circle called upper strict. So again, when you consider only like constant sheaf and so on, then upper strict differ from upper reduced by just some shift, and that's all. But for some technical reason, I actually consider this upper strict thing. And another way to say the difference is that they differ by some Poincare or Verdier duality. So essentially, it's just some tensor product, but for most purposes, just differ from the usual one by a shift. Okay, so whenever you have a monoidal structure on some category, then you can consider the carrier commutative algebra objects on it. In fact, right? So kind of chain complex is such a usual monoidal structure, so consider carrier commutative algebra on vect. And then, so now, right, when you pull back a sheaf, you know that when you pull back a tensor of two vector spaces, then you get a sheaf that is the tensor of the pullbacks. So another way to say that is that upper strict is symmetric monoidal, and so it induces a functor between the carrier commutative algebras. So it just upgrades to a functor like so. And then this functor actually commutes with limits. And so by some adjoint functor theorem, you know that there exists a left adjoint. So I wrote F lower to note that it's actually not F lower strict. So here's the deal. So suppose I have, so first of all, let me say some terminology. So if A is a commutative algebra object, so a sheaf of commutative algebra on X, then F lowers question mark of A. This is say we call this the factorization homology of X with coefficients in A. So this is a simplified version of what people usually say, factorization homology, but it suffices for our purpose. And now let me say one more thing about this F-low question mark. So right at the back, from the definition of F-low question marks, the fact that it's a left adjoint, you can see formal nonsense that you look at the, take a sheaf V and look at the free commutative algebra objects in the category of sheaves. So you get some commutative algebra object and you do this factorization homology game, then this is actually the same as F lower strict of V. F lower of sim V. Sorry, I'm mispronouncing. F lower strict of V and then take sim. Right, so F lower question mark of a free thing is the free thing of the F lower strict. Right, so factorization homology of a free thing is just free commutative algebra object generated by the usual cohomology. Right. Okay. In our twisted case, so the twisted is not so different from the non-twisted case. So again, X not to a point like before, but now you just enrich everything with an FB action. Right? And you also have a pair of adjoint functors. And then you can do the same thing. So this is like the category of sheaves of twisted commutative algebras over X. And here's essentially the same as above. Then you do this. And you also have a pair of adjoint functors. Okay, so far it looks rather useless. I mean, I defined it in a certain way. And I just like, I mean, I can define anything I like, but so what's the point, right? So the point is that here's a theorem. Let's say the following. So Cx mod x to the n. So Cx, right, is an algebra, a twisted commutative algebra. And then I just truncate it. I just keep everything of at this end. And I do pullback. And then I take its factorization homology. Then this thing is actually the same as the cohomology of Pn of X. Right, so the theorem says that the factorization homology with coefficients in this truncated twisted commutative algebra is the cohomology of the generalized configuration space. So, right, so this n is the same as this n. And here, X is in graded degree 1 and in cohomological degree. Okay, so here is D. So really, I will put 2 here. So the reason is that I usually think about scheme and varieties, and complex dimension is half of the usual dimensions. Normalization that I use, so I put 2D there. And the reason why it's 2D there is because I had this upper strict thing, and I said the upper strict differs from the usual pullback by some shift, and this 2D is just to compensate this this thing. Okay, so that's one line that I've been saying. So let me say it right away. That literally is actually not, it's not quite the cohomology of configuration spaces. So in the case where it's smooth and compact, then it is. When it's not smooth, then it's essentially Borel-Moore homology. And when it's not compact, then I have to change my formalism slightly to make this formula true. Namely, I have to modify this formula a bit to make this formula true. but there's some technical details that's not quite relevant for us. Okay, so here's the intuition of why this theorem holds. So here essentially, so the reason why x to the n is there is essentially to kill, disallow locus, namely this delta n. Right? So remember, p, k, and x is x to the k minus this n. So this n is there to kill this delta n part. So I think if people are interested in hearing the proof of this, I can sketch it maybe after I finish everything else, maybe after the talk or something, but this is somewhat technical and I'm not sure whether everyone is interested in hearing this proof. But this is the first input into our result, right? So this gives us the first goal, right? This equip this guy with the structure of a twisted commutative algebra just from this formalism. Okay, so the second part, right? So far I've defined fertilization homology as something abstract. Obviously, I mean, it looks cute, but I mean, it doesn't do anything if we don't say anything further. So to compute anything, we need something called causal duality. Okay, so just be reasonable, some nice symmetric monoidal category. Then you can look at the category of commutative algebra objects in C. And on the other hand, you can look at the category of something called co-Lie algebra in C. So for technical purposes, co-Lie appears, but you can think of it as, if you just think about chain complexes, then just think it's something whose dual is a Lie algebra. So when I say Lie, I really mean differential weighted Lie algebra. And so this theory of causality went back to Quillen and then further developed by Ginsburg and Kapronoff, and then I guess further developed by Francis and Gatesbury. But the point is that there's a pair of joint functors. There actually is an equivalence. So if you always have a pair of joint functors, but when C is reasonable enough, then it's actually an equivalence. And I will just name them. I call this right adjoint, co-chef, meaning take the cohomological Chevrolet complex. So this Lie cohomology functor. And the other one is called co-prim, but it's actually shifted by one. Okay. So before explaining what these are, I will say the following. So this thing works for when we take C to be shift of X FB or vect of FB. So this thing that you can apply this theory to the situation that we're interested in. Okay, so coprim. So let me say something about coprim. So coprim, so let A be commutative algebra. So the intuition behind coprim is the following. So you look at, so it's obtained. So correctly killing everything of the form A, where A and B sign A. Right, so if an element, so again, this sentence only works when A is non-unital, right? Because if you have one in there, then obviously everything is that times one. So I mean the situation where A is not a unital commutative algebra, doesn't have a unit. So this is say that co-pays from A by just like removing, in a certain sense, removing everything that of two other things. And if you do this correctly, then you obtain this thing called derived Coopers and Van der William. Okay, so to actually define it, okay. So let's see, one more thing, sorry. So one more thing is that this co-prime thing, so this is directly computable. But if you shift by one, so you have to apply this, whatever it is here, you shift by one, you obtain this functor that I write co-prime one. So the number one here is about shifting to the left by one. So left being smaller cohomological degree. Okay, so the way you actually define this co-prime thing is by some, essentially you form some bar, some superficial object, some bar resolution of your algebra, and you take its co-limit or geometric realization, and that's how this co-prime is defined. So it might sound a bit complicated, but in fact, we only need two important points about these two functors, co-chef and co-prime. So these are the only technical input we need. So causality exchanges free and trivial objects. So what I mean by, suppose I start with say a free commutative algebra, right? And I apply co-prime to it. Then I just recover the generators, right? So then it's just V shifted by one. With the trivial, it's not the chain complex being trivial, but the algebra or co-algebra structure is being trivial. Or if you apply homological stability complex to a trivial, so let me call it co-triv because it's really a co-algebra, a trivial Lie algebra obtained by V. So trivial Lie algebra means that all the brackets are zero. Then I just get this V sigma V shifted by -1. So shifted to the right. So that's the first part. So this exchange is free and trivial objects. And so this is not hard. When you write down the definition of causality, this just falls out. The hard part is to prove there's an equivalence, not this. Okay. And then so that's the first part. And then the second part is essentially say that we want to be able to reduce. So both of these functors have natural filtrations whose associated gradient is free. So what do I mean by that? What I mean, so for example, consider co-chef of some complicated Lie algebra G, right? And it says that there's natural filtration, so there's filtration I. So let me not say I, but say one not into the other, such that when I take the associated gradient, and obviously taking direct sum of all of them together, then this, which is recovered for me, C of G shifted by -1. Right, so it has a natural filtration whose associated gradient is this thing. So if you like spectral sequence, then this reads like this. You have a spectral sequence whose page 1 is this, and whose page infinity is the thing that you actually care about. Right, so this filtration gives you this sort of spectral sequence. So page 1 is like something very simple, and you hope to use that to gain information about the thing that you actually care. And for purpose homological stability or estimating where the support of these generators are, this suffices. Modulo some theorem about like finite generation and the variance and so on, which I will hopefully get to shortly. Okay, so now I just told you two different things. One is causality that looks fertilization homology that looks abstract but has something to do with configuration spaces. Now, the next thing I want to talk about is how the two are related. So, first thing versus causality. Okay, so here's a very nice fact. So let A be a sheaf of twisted commutative algebra objects of X, and I want to take its factorization homology, lower question mark A. Then you can do the following. First, I can just look at the generators of A derived indecomposable or causality. So look at co-prim of A. So now this has a natural structure. It's a Coley algebra, and do the usual push forward. And now this is an object, Coley inside vect. So twisted, differential graded Coley coalgebra, and then I look at its homological stability complex. So again, this is actually quite formal. This when you set up the theory correctly, then some diagram chase, essentially of the form like if left adjoints commute, then right adjoint also commute. That sort of thing will give you this statement. Okay, so in particular, the keys that we actually care about, right, is the following. Right, this is what we care about. So that's going to be co-chef, F-low-strict, co-prim 1 of Cx, mod x to the n. Okay, so now that means that, so with all the filtration and super sequence I talked about earlier, essentially that reduces to trying to understand the derived indecomposable of this very simple thing, right? I mean, at least it looks simple. At least it looks simpler than the problem that we started with. So now the goal is to understand the derived indecomposable of Cx mod x to the n. Okay, so let me note this object an. So it's a Coley coalgebra. And for the rest of the talk, I will just do it for the case equal to 2. But most of the things that work for other n, essentially verbatim. So this is the case of just order configuration space and not going to generalize anything. Okay, so in this case, right, it's actually very simple. This is Cx mod x squared. Right? This is a trivial algebra object generated by one element. Right, so I'm going to say the unit out the C, and you look at this x, right? X multiplied with x is 0. So this is a trivial algebra object. And so by what I said about causality, see the A2, which is co-prim of this, is a free, or rather co-free, Coley algebra, again, in the twisted setting, generated by one element. Okay, so essentially, how do you form free Lie algebra? You start with V, right? And to get a free something out of it, you do V tensor to the K times. And then you time something else. But some vector space, so let me call it scientifically. Essentially, you have some vector space, and then you tensor with this V to the K, and you take direct sum for all the K. So essentially, the point I'm trying to say is that this is where the support is. It's just essentially just tensors of V. So what I mean by that is that suppose you start with V star, right? Then the freely of that is just things that are support on this line. So this is weighted degree and homological degree. Okay, very good. A2, right? So we call the X is in weighted degree 2. Sorry, I'm saying something else. Degree 1 and homological degree 2D. And then co-prime, you get that X, but you shift by 1. So co-prime of 1 of this guy, right, is essentially generated by X, but shifted by 2. So the picture looks like this. So you have 2D minus 1, and you do this. So it's supported on this line. So that's what the thing looks like. Okay, very good. So now we understand this one. The next is to understand its cohomology. Right, so again, up to this compact versus non-compact thing, its cohomology would be C, the string complex of X, the coefficient in the dualizing sheaf. So this is just the constant sheaf, but shift to the left by 2D. Tensor with our A2. So this thing we have for the picture. So essentially you have this, right? But now you have extra 2D cohomology. So you essentially, let me just reuse this. So you have something look like that. So this is -1. Okay, and now you want to apply co-chef to it. And I know I said that there's a filtration whose associated is just one shift to the right. So let me draw the one with to the right. Will look like this. So we support along this line. So this is 0, 2D, and this is 2D minus 1. So this is the next step. So this is the support of this guy after shifted by 1 to the right. And so what we do essentially, the thing that we actually care about is roughly look like seam of this guy. So some cone that looks like it's a support. Okay, so now I have like 1 minute left. Maybe can I have like 3 more minutes? And then hopefully, let's see.
Go for it.
So where does representation? Yeah, okay, thank you. So where do rep stability come from? From this picture. So essentially what we do is that, okay, so you have these generators, right? Let me delete this. I have these are the generators and a this sample. And then this guy is a generator, so X on the whole thing. So this guy actually corresponds to H0 of X. And so after taking co-chef and whatnot, it just acts on everything. And that gave me a map to witness to formulate higher representative stability. And now suppose I want to compute Fi homology, right? Just remember this thing. And then when C is some co-chef or something, this is something else. That essentially the degree 0 part of this guy at weighted degree 1. Then when you do this relative tensor, all that you do is you get co-chef of A2 prime, where A2 prime is A2 by just deleting this guy, and that's it. And then you can continue and do the next guy. And essentially, you can obtain all the bounds for all the hyper or higher analog of Fi homology. Okay, so that sounds fun, but here's some concrete that you can essentially prove using this strategy that I just mentioned. scheme of lim D, so think 2D, and then fix number C0 greater than equal to I greater than equal to 0, and N greater than equal to 2. And then C0 is less than equal to 2D minus 1. So some number. So then this number is there, is that when you do this game, right, at some point, and you delete that point, right, it doesn't help. It doesn't say much about finite general because this thing here is above low. So this number there is for that sort of thing. Then you do this thing. So let me write down first and see what it means. Okay. Okay, so first of all, this object is obtained just iteratively delete these two things I mentioned above. So after C0 minus 1 step, finitely generated module over sim of C0 of X with some shift, putting gradient to 1. So namely, when T is big enough, the action of this guy on this guy will give you some subjectivity that you care about. So that's the, yes, 3 minutes over. I'm sorry for the end. This is the end of the talk.
Thank you. Do we have questions for Quoc?
I have a bunch. Can I start with the first one?
Please.
Are you using like Noetherianity of some twisted
Yes, thank
algebra?
you. Yes, so this is definitely Noetherian. I need some Noetherian of these algebras. Yes.
Okay. Does someone else want to ask a question, or can I?
Are TCAs?
Sorry, can you say it again?
Is this just is this the TCA that is generated
Yes.
in degree 1 by this thing?
Yes.
So you don't need any algebras that are TCAs that are generated in degree 2 or higher?
No, at least from what I said, nothing is in degree 2 higher. So there's some game you can play. You can try to pick this guy. Right, so what Müller and Jenny, Wilson and Müller did was essentially picking this guy. But they use a different map. So they bring in the kind of orbit of two things, infinity. So for example, that map doesn't exist when your thing is compact, at least as written. But let's have some vanishing property that's somewhat complicated to state. But once you have that vanishing property, then you can also get a stabilizing map that is obtained by multiplying by this guy. So this guy is like H1 of configuration space of 2 points of your thing. So
one comment is, so Quoc can construct, or Near and maybe could construct, following the tradition of randomly deciding between last names and first names, construct maps coming from any homology class in configurations of points in the manifold. And if you look at the configuration space of 2 orbiting points in a manifold, that is usually 0. Let's say for
yes,
or it's often 0, but it's non-zero in configurations of points in a disk. So you can sort of what Jenny and I do, we use homology of configurations of the disk, so then we can see 2 points spinning around. But if you're looking at the manifold, like in your manifold is a torus or something, that homology class will be 0. Or so in cohomology, there's no co-cycle that detects it or whatever. So you sort of don't have those maps. Yeah, so you don't have a favorite. Peter, you probably don't have a favorite class in like H1 of 2 points in a surface that you would want to like plug into their machinery.
Also, I want to make a comment that
The thing I'm confused about is why you get a TCA generator in degree 1 if it involves a module with, I don't know, shouldn't you have like endpoints involved or something? I don't know. That's what I'm confused about.
different flavor from what Wilson and Miller did. So this is about multiplying with like stuff that has multiple points. So usually in this picture, the usual stability comes from multiplying with essentially H0 of your space. And now you try to multiply with H1 of your space and H2 of your space and so on. And you're not bringing more points in, but you somehow use the cohomology of X itself to act.
Peter, maybe you should think that you're in higher dimensions. So there's slope 1 stability instead of slope 1/2 stability. So secondary stability should be slope 1 and not slope 1/2.
Yes.
I don't know if that's related.
Yes, I think that's
you do secondary stability. You don't do any like tertiary and higher order stability. Is that right?
Can you say that again?
Do you do higher order stability in this setup as well, or is it's precisely secondary stability?
Then you can also to formulate. So you don't always have that map, but if there are some conditions to satisfy, then you can use this guy over there to actually do the secondary in your sense, meaning like about 2 points. And if you have even more stuff, then you can do doing in 3 points and so on. But that requires more and more special assumptions on your manifold. So in the most degenerate case, like the nicest case, is the case where something called, I think it's called cyclic or something, where essentially it means that the algebra structure on your cohomology of X is just like nothing, just like vanishes. Then all of these co-chefs disappear and just have sin. And then you have all the actions that you like. And you can multiply. I mean, in that case, then you just know exactly this is just a freak TCA. So you can say anything you like. But when you don't have that, then you have to kind of be careful what class you're allowed to multiply with and so on. I don't know. Does that hopefully answer part of your question?
Can I take another question?
Sure.
Okay, so there's a couple about the algebras. So first, when you say commutative algebra, do you mean like up in the homotopy sense?
Yes.
Okay, and the second, so the algebra you defined for us was CX mod X squared. So that has a unit.
Yes,
So
when
when you
I
pass to incomposable, do you remove the unit?
Yes, I just removed the unit. In fact, I just work with like non-unital from beginning. And I just put it in there. Okay, so here's the thing. Causality plays nicely with non-unital stuff. But when you write things like relative tensor, right? We're just more used to writing with unit. Like when you write like this tensor, this over something else, it's just like part of at least my training that you just have unit there. So whenever such a thing appear, I just put the unit in. And that doesn't cause any problem because I mean, non-unital algebras are the same as augmented unital algebras. And so I can pass freely back and forth. So that's kind of something that you have to do to be both, to have both something that looks familiar and something that works in causal.
Great. Okay, so that's a 2-for-1. And maybe my last question is: does the formula you told us about with factorization thing is the same as chains in the configuration spaces? Does that help me understand what Ben Knudsen maybe tried to explain to me a while ago? I mean, Ben Knudsen has this formula that I never really understood. So does this help me understand it?
So I guess here's the difference. So there's a different kind of causality called EN causality. So the kind of causality is commutative and linear algebras. There's another between something called EN algebra and EN algebra. So EN operators are causal self-dual. And so now here's the thing that Knudsen did. So to study configuration spaces, he studied factorization homology with coefficients in a free EN algebra. So that's his theorem. And the thing is that when you look at free EN algebra, it actually comes naturally equipped with a commutative, or rather co-commutative, co-algebra structure. So now, when you apply the EN thing, right? You go from co-com algebra of EN algebra, right? Causal dual will give you something like co-com algebra in say EN co-algebra. Or if you take another dual, you will get com algebra in EN algebra. And then essentially this commutative thing just absorb this EN by some sort of like Ekman-Hilton stuff or do additivity, then you just get this. So this thing is just the same as commutative algebra. So the claim is that suppose you start with free EN, and you chase through this, you will just get trivial algebra generated by V. So that's why I see this EX mod X squared shown up. And it's just simpler to work with this. Once you realize this, then you can just start with this instead of playing with free EN algebra. It's just simpler. But essentially, it's the same result, but up to causal dual.
Thank you.
Do we have any more questions? Let's thank the speaker again.
Yeah, thank you for inviting.
Great. And now traditionally we have a social hour after the talk. So earlier we would switch from this Zoom room to a different Zoom room to make it official, but then we decided that that was actually unnecessary. So I'll just wave my hands and declare us to be in the social Zoom room now.
We should probably unshare the screen though, so we can actually see each other.
Oh, good idea.
And probably stop recording.
And stop.
Oh, that's
recording.
really important.
Yes, good point. Am I the one recording? Do I know how to stop recording? Oh, here it is.